The aim of this lab was to experiment with simple circuits by applying our new knowledge of electrostatics, electric potential, and circuits. Firstly, we were tasked to form a circuit that could successfully light up an LED with a push switch. Secondly, was to build a voltage divider circuit. And thirdly, was to investigate the charging and discharging of a capacitor while varying the resistance. Each group was supplied with a breadboard, a multimeter, an assortment of 1 kiloohm, 10 kiloohm, 100 kiloohm, and 1 megaohm resistors, a light-emitting diode, known as an LED, a 470 microfarad electric capacitor, 4 male-to-male wires, 2 push switches, and 1 9-volt battery with a clip. There were some initial struggles in figuring out how we were going to wire the circuit with regards to the position of the components on the breadboard and their connections. Initially, for task 1, we struggled to understand where to integrate the push switch into the circuit. After planning our circuit using a diagram and first building a circuit without the push switch involved, we were able to figure out the integration of the switch. Eventually, we came to realize that the switch should come before the resistor and LED in relation to the conventional current flow from positive to negative terminals. So, we constructed a push switch circuit as so. A 9-volt battery supplies voltage to the circuit, where a push switch, a 10 kiloohm resistor, and an LED are all connected in series. Here is our circuit, followed by our circuit diagram. We observed that when the battery was connected, the LED did not light up. However, when we pressed the switch down, the LED lit up. And then, when we stopped holding down the push switch, the LED stopped emitting light. The reason this happened is due to the switch. The function of the switch is to either open or close a conductive path. In our case, when the switch wasn't being pressed, open, no current was flowing through that path. When the switch was being pressed, closed, current was allowed to flow through that path, and thus the LED lit up. For task 2, we planned our voltage divider circuit by creating a circuit diagram first. This involved just our 9-volt battery and 2 resistors connected in series with it. In order to test our voltage division, we connected our multimeter in parallel with the first resistor, using 2 probe cables, and then followed suit with the second resistor. Here is our setup. We observed that the voltage across the first resistor was 7.94, and the voltage across the second resistor was 0.79. Using the equation V out equals V in times R2 all on R1 plus R2, we confirmed the voltage drop by calculating the expected voltage and comparing it with the voltage measured. This is how the equation was derived. The V out on the first resistor was 9 times 100 times 10 to the 6, all on 110 times 10 to the 6, which equaled 8.1 volts. V out on the second resistor was 9 times 10 to the 6, all on 110 times 10 to the 6, which equals 0.81 volts. These values agree with the measured voltage divided despite inaccuracy of 0.2 and 0.02 volts respectively. This produces an uncertainty range of plus or minus 0.1 and 0.01. The way a voltage divider circuit works is that it produces an output voltage that is a fraction of the input voltage. This is the result of the input voltage being distributed between the 2 series resistors, thus producing an output voltage between them. For task 3, we initially struggled with how we were going to implement our capacitor into our circuit. After deliberation and circuit planning, we came to understand that the capacitor should be in parallel with the resistor, LED, and, in order to demonstrate capacitor charge and discharge, a push switch must also be a component within the circuit, as well as the 9-volt power supply. Here is our circuit diagram, and here is our breadboard circuit. We observed that when the push switch was held, the LED lit up and was getting brighter. When the switch was open, the LED began to slowly dim until it was no longer emitting light. The theory behind this is, when a capacitor is attached to a battery, it will slowly develop charge on each plate as electrons build up on one polarized plate and then exit the other. Once the switch is open, this difference in charge between the 2 plates is discharged to the LED component. Once this occurs, charge slowly transfers from one plate of the capacitor, moving through the circuit and onto the other plate, until the charge dissipates. When we varied the resistor size, we noticed that the larger the resistor, the slower the charge and discharge rate, meaning the LED took longer to get brighter, but was lit for longer. This is because the resistor slows the rate of charge by limiting the current that can flow into or out of the capacitor. In conclusion, after some practical uncertainties, our group successfully displayed a push switch circuit, a voltage divider circuit, and was able to recognize the effect of varying resistor size on a capacitor circuit.